In this video, we're going to look at example 3 and graph it, evaluate it, and then look at examples 4, 5, and 6, and I'll let you do 7 on your own. Although the key to all of these is on the canvas. So when we look at example 3, we have kind of 3 pieces of this piecewise function. The first is the 3x minus 1. It's a line with a slope of 3 and a y-intercept of -1. So just real quick, we can imagine what that should look like. It has a y-intercept down here at -1. It has a slope of +3, so it should go up 3, right 1, up 3, right 1 forever. And you could kind of trace it backwards. Instead of going up 3, right 1, you could go left 1, down 3, and get to another spot on the line. We would have something like this. Okay, this would be the line 3x minus 1. But according to the restriction, we're only graphing it for when x is less than -1. So if here x is -1, then all the stuff that's less than -1 is valid for this graph. So we'll keep all the stuff that's less than -1 and get rid of everything else. Okay, so now when I go to my actual graph, I'll remember that, okay, it normally would have gone through the y-axis at -1, and with that slope of 3, it would have gone up 3, right 1, up 3, right 1. Or, again, since we can trace it backwards, it would have gone down 3, left 1, and crossed through this point, down 3, left 1, and crossed through this point, and we would have this. Okay, hopefully you agree with the choice to cap this thing off with a open circle because of the strictly less than. And so we just kept this portion of the graph, and that's how we got here. Okay. We also, in the second piece, have the function y equals 4, which, remember, y equals 4 is just a flat line at a height of 4. So we're going to have this graph, but we're only keeping the stuff between -1 and +1. So y equals 4, 1, 2, 3, 4 is a line that just goes forever right and forever left at a height of 4, but we're cutting it off at -1 and +1, and we're just keeping this section in here. And because of the or equal to at -1 and +1, so when x is -1 and +1, we just cut off everything and just focused on that section. And the last one is y equals x squared, but for x greater than 1. So the last thing and you don't have to visualize this if you already kind of know what's happening, but for those of us who are less familiar, we would imagine the graph of y equals x squared, which looks something like this. But we're just keeping the stuff for when x is greater than 1. So if here is 1, then all the stuff greater than 1 is all the stuff to the right of that line. So we would keep just this segment here. Right? It would go through 0, 0. It would go through the point 1, 1, 2, 4, 3, 9, and would look like this. Okay? And again, capping it off with a closed circle. Okay, so I just kept this section of the graph. I said closed, I should have said open, sorry. Okay, and this is our piecewise function. And with practice, you won't need to draw this over here. You'll just kind of understand that we're imagining the whole function, but then just focusing on a specific section of that function. Okay. Evaluate, we've learned in the last video that you could plug in a 3 in for x into one of these functions, or plug in a -1 in for x into one of these functions. And as long as you pick the right one, because we can't plug in a 3 into each of them, we'll get potentially 3 totally different answers. We want to be able to plug that 3 in for x, but only into the right one. And so we would want to look at these restrictions and see which of these, when x is 3, is the one that's actually true. And it's going to be the bottom one. Right? 3 is greater than 1. So that's the value I'd plug in here, and 3 squared is 9. Okay. For the rest of these, let's just look at the graph. F of -1, so when x is -1, y is 1, 2, 3, 4. you may be tempted to say -4, but because of that open circle versus closed circle, we're going to say that when x is -1, y goes up to 4. What about when x is 0? When x is 0, y is 4. And when x is 1, y is 4. Okay, again, we ignored the open circle and focused on the closed circle. Awesome. Okay. Let's look at example 4 here. It says, write a formula for the piecewise function. Write a formula for the piecewise function. Move the camera up a little bit. Okay, so hopefully we can see that. Okay, so when we write formulas for piecewise functions, I usually call it f of x equals, and then we get to practice these fun little braces here. And in this case, it looks like there's 3 pieces. We've got this linear piece, of course the quadratic here, and then we've got this constant function. So let's start with, I mean, you could start wherever you want, but we'll go left to right. So what's the equation of this line? Well, to write the equation of a line, it's almost always going to be y equals mx plus b. So if you can find the slope and the y-intercept, then you have the equation. So what's the slope of this line? Well, to find the slope of any line, you can pick any 2 points that you know the line goes through. For example, I know it goes through this point and this point. And then just find the rise over run going left to right, and it looks like it goes up to right 1, up to right 1. So the slope for sure is 2. So we have the function 2x plus whatever the y-intercept is. But the y-intercept is not pictured, but I hope you'll agree that if it were to continue on, it would eventually cross the y-axis somewhere up here. And it's our job to figure out what that is. Okay, and well, let's kind of just use our slope here. If it goes up to right 1, up to right 1 every time, then if it goes up to right 1, up to right 1, so look where I'm at a height of 7 currently. If I go up to right 1, I would be at a height of 9. And if I go up to right 1, I would be at a height of 11. Okay, so I'm just using that slope, that constant slope of 2 over 1, up 2 over 1, up 2 over 1, until I get above x equals 0 at a height of 11. Hopefully you're okay with how I found that. Okay, but with all piecewise functions, it's not enough to write the equation. You also have to specify the restrictions. Where are you allowed to graph this? So, in case it was unclear, this is an arrow. So it looks like we're allowed to graph this from -infinity all the way up to when x is -4. So when x is less than -4, we're allowed to graph this function. If x is greater than -4, we have other functions that have taken over. But if x is less than -4, this is the one that we're graphing. Okay? Now, you may ask, what happens at -4? And because of this closed circle, I hope you agree that this should be less than or equal to -4. Cool. Over here, there's a bit of a problem. The graph should look like this, so just go ahead and draw that in. Of course, if that wasn't there, it might look like it failed the vertical line test, but we'll just put that open circle there. That way it's clear kind of which function we're referring to. So, all right. Let's look at this middle piece, this quadratic piece. Maybe before I write the function, I'll just go ahead and knock out my restrictions. It looks like the quadratic here is just between here and here on the x-axis. So that's from -4 to +2. From -4 to +2, we have the graph of the quadratic. Anything that's outside -4 and +2, other functions have taken over. So we have an x that is less than 2, but bigger than -4. Okay, less than 2 but bigger than negative 4. And because of the open circle above an x value of negative 4, we'll leave that symbol as is. Because of the closed circle at positive 2, we'll go ahead and put that in here. In later examples on a test or something, this mistake isn't made. So it'll be abundantly clear that this was a closed circle and this was an open circle. So forgive me for it not being clear on the notes. Okay. But we know the restrictions, so we're graphing some quadratic between negative 4 and 2, but what quadratic? This is actually kind of a tough one, maybe even tougher than I wanted it to be, but that's okay. It looks like it's the quadratic that's been moved down 2. And if you were going very quickly, this is all you would write. It's definitely a quadratic, and it's definitely been shifted down 2 units, so that's okay. But normally, and look at this, normally the quadratic would go over 1, up 1. That's curious. It looks like this one just goes over 1, up a half. And normally, the standard quadratic goes right 2, up 4. 1, 2, 3. So normally it should, if it was just x squared minus 2, then from this vertex it would go right 1, up 1, right 2, up 4, right 3, up 9. But in this case, it's only going right 1, up a half, and right 2, up 2. So it's half of what it should normally be increasing vertically. So it has been vertically compressed by a factor of 1/2. The normal change in y values, 1, 4, 9, have been cut in half. So instead of going up 1, it just goes up a half. Instead of going up 4, it just goes up 2. Instead of going up 9, it would just go up 4.5. So everything's been vertically compressed by a factor of 1/2, which is admittedly pretty hard to see there, but something you want to look for just in case. I don't anticipate you would see an example like that on a test or a quiz that's so tricky like that, but something to look out for sure. Okay, and then the final piece is this piece that looks like it starts here at an x value of 2 and continues on forever. So as long as x is greater than 2, we're going to have this constant function, which is the function, it's just a flat line at a height of 2, y equals 2. Okay. Awesome. And that's it. If you want to put little commas here to kind of indicate where the function ends and the restriction begins, that's not a bad idea. Okay. Let's do maybe 5 part B. Let's look at this part. I'll let you do this one on your own and refer to the key. So I'm not going to do this one, nor am I going to do example 7. So I'll do 5B and 6, and then we'll be done with the video. So we have this piecewise function, so hopefully I can fit it in here. It looks like, so it's definitely an absolute value function, but the directions say write the absolute value function as a piecewise function. So normally we would just call this one absolute value function. But if we thought about it, we realized that we could write it as 2 lines. And so we will. So there's going to be 2 pieces to this function. Let's look at the first piece. It's a line that specifically has a y-intercept of -2, and it looks like a slope of down to right 1, so a slope of -2. So the equation of this line is -2x minus 2. It has a slope of -2, down to right 1, down to right 1, down to right 1. Slope of -2 and a y-intercept of -2. Okay? And this function, so I'll put my comma to end the function and start the restriction. It looks like this function is for all values x that are less than 1. It is at the x value of 1 where the first line stops and the second line begins. So as long as we say x is less than 1, we've covered our bases, because this line does not go down forever like it normally would. It goes down and then stops when x is 1. So as long as x is less than 1, we're allowed to graph this line. What about when x is greater than 1? When x is greater than 1, what happens? Well, that's a different line with a different slope and a different y-intercept. The slope, I think you'll agree, is also up to right 1, up to right 1. So the slope of that line, that second line, is 2. So mx plus b, that's 2x plus b. What's the b, though? Well, the y-intercept here isn't necessarily pictured. This line would continue on and eventually cross the y-axis somewhere, right? It would be our job to figure out where that is. Because, of course, it got cut off, so we can't see where it crosses the y-axis. But if we were to imagine that it didn't get cut off, we can kind of trace backwards and figure out where that is. So let's look. Okay, here we are. If we go left 1, down 2, we're at a height of, let's look, -1, -2, -3, -4. So this spot right here is at a height of -4. So I went down 2, left 1, and got to -4. If I went down 2, left 1, I would be right on the y-axis at a height of -6. Okay? I hope you see that. And we're very close to done here. I would encourage you to think on your own about the one thing that I'm missing here. And it actually involves this restriction. Hopefully you caught it. Because this function is for sure defined at this point, we're going to need one of these at least to be have a greater than or equal symbol, that line underneath the inequality. The question is, which one gets it? And the answer is, it doesn't matter. You get to pick. So maybe this one. What does matter is that only one of them gets the or equal. If they both got the or equal, then when I asked you what happens when x is 1, you might plug it into both functions, and that could be problematic. Okay, so we want to say that yes, because the function is defined at 1, one of these has to get an or equal sign. So just pick one. So I picked the top one. If you picked the bottom one and left the top one just strictly less than, that would be okay as well. Okay, there's our answer. Last one here, this word problem. A store charges $15 per t-shirt for orders of 50 or fewer, $13.50 for t-shirt orders 75 or fewer, but certainly more than 50, and $12.50 per t-shirt for orders of more than 75. Write a piecewise function representing the situation. So let's let C be the cost and T be the number of t-shirts. Then we can write a function as C of T. So the cost given the number of t-shirts. So if you tell me how many t-shirts you've sold, I can tell you the cost with this function. So it's pretty straightforward, I would think. If you bought 10 t-shirts, how much did it cost you? Well, you would take $15 and multiply it by the number of t-shirts you bought. So 15 times the number of t-shirts you bought. If you bought 2 t-shirts, it would cost you $30. If you bought 3 t-shirts, it would cost you $45. And so on, all the way up to 50. Because at 50, the price changes. Okay? So it's 15 times the number of t-shirts you bought, but only if T is less than 50. Is it less than 50 or less than or equal? Let's look. For orders of 50 or fewer. So it could be exactly 50. Okay? So if you bought 50 or less, it's going to cost you $15 times the number of shirts you bought. But if you bought more than 50, it's $13.50 times the number of t-shirts you bought, but only for t-shirts that are number of t-shirts more than 50, but less than or equal to 75. So again, of 75 or fewer. So if you buy anywhere from 51 to 75 t-shirts, it's going to cost you $13.50 times the number of shirts you bought. And then lastly, it's $12.50 times the number of t-shirts you bought, but for orders of t-shirts that are greater than 75. And this function right here would represent the cost of your order given the number of t-shirts. You tell me how many t-shirts you bought, I can plug it into one of these depending on, again, the restriction, how many you bought, and I can give you the cost. Awesome. check example 7 and example 5a against the notes, and that's it for these videos.